Hey there, math fans. Have you ever wondered what the formula is for a mortgage or a mortgage payment and where it comes from, or how much money you have to put away so you have a certain amount of money when you retire? These are very important questions that we all encounter. In the business math class we teach, Math 111 at UW, those formulas come up more as an opportunity for us to talk about exponential functions. For years in class, I talk about examples from my life. My student loans, my home mortgage, and I give the students a handout. And I always assume the students just threw it away. Most of the time they're like, what even is a loan, and you're 18. But I have evidence that somebody was listening. So this morning as I was walking through the university district, a student stopped me, which has been happening more and more, which has been great because we've been riding the light rail. And the student said, Dr. Lovelace, 4 years ago I was in your Math 111 course. I was trying to do nursing at the time. It was they said it was one of their favorite courses at UW, which always makes me think, what do they do other courses like? But thank you for that. And they said they did ultimately switched into public health. I think the student's name was Lucia from, CTech area? But she explained how she's a first-generation student, and after my class, she went home and taught her family the mortgage formula and used my information, and she's tutoring her younger sister in math, and she's studying public health, and so it was lovely. Lovely to think that in some way I matter to someone and that somebody was listening. Which is why I'm making this video. So this is for this student, but also I think this is of general interest. So I'm going to share a little bit of what I do, add a little math here in the middle, and then answer this question, when can we retire? But maybe if I'm of value, maybe I don't have to retire so soon. So in that course, we talk about this situation. Situations where you're making regular payments to something and building up the value, like saving for retirement, or you're paying something off or reducing a balance. And we call those future value or present value questions. I'm going to try not to get too technical. I remember students when I teach the course, they're like, I can't tell if the balance starts at 0 or ends at 0. And I'm like, you can't? Those are pretty different. But I get it. Sometimes the way things are stated, and if you don't have life experience, I can see where that can be tough. But I pretty much can tell when I'm starting with 0 or ending with 0. Anyways, here's the scenarios. Imagine you're starting with 0. And I'll do a couple simple examples. Then I'll prove the formula. We'll get to use geometric sums. That's kind of fun. And then I'll say a little bit of examples from my life and show you some resources. So I hope this is interesting. And thank you to my student for stopping me today. I never would have thought of this. So let's say we start to we have some bank account. And for this example, let's say they just give us 2% per year. Okay, so we'll get to that in a second. But let's just say these are years, year 1, year 2. We're going to make it really simple, not like they actually do at the bank. These are the two formulas I'm talking about. There's even some subtle other pieces, but these are the formulas. This is the formula you use for loans. It's also the formula you use for spending your retirement. There's a funny question you have to ask yourself, which is, how long do you want to live after retirement? If you don't want to live that long, you don't need to save that much. It's a morbid conversation. And this is saving for retirement. And these are things where we have regular payments. Okay, so imagine we do the following. At the end of the first year, we deposit $100. So we started with 0, and we deposit $100 into our account. So at that point, the balance is $100. The way interest works is for this part, we're going to assume this. At the end of the first year, they're going to add 2%. Now, in my class, we have to talk about this a little bit. Students seem to have a misconception about percentages a lot. And so we have this discussion of what is 2%. of 100. And you should, another video I have to make sometimes is if you ever have to do percentages, like if somebody said, what is 23% of something? And it's not a nice number, you just figure out 10% and 1%, and then you use those to figure out whatever you need. Now in this case, 1% is $1. So I made the numbers nice. And 2% would be $2. Okay, so all you did was that. Sometimes we call that a lump sum. You just put that money in there. And then you would have 102 here. Then you have this idea of compounding, which means you're going to have to add 2% again. So how do you do 2% of 102? Well, 1% would be $1.02. So 2% would be $2.04. So then you're going to have to add $2.04. Boy, this is seeming really complicated. So if you had $2.04, and I have my calculator out here, so we basically did 100. And most students, when they try to do this, they add, and they do 0.02, and they do times 100. And I find most people want to do it that way in steps because that's how we think about it. But there's a better way. And this is one of the key observations, which is instead of thinking of it as 2% added on, instead of thinking of it as an additional 2%, think about it as 102% multiplied. Additional 2% is the same as saying 102%. Let's see if what I'm saying is true. Okay, so now we're going to do 100, but this time we're going to multiply by 1.02. 102%. That interpretation works way better. Okay, so let's jump a little further. We're going to do 102% again. So what's cool here is you can just hit times 1.02. Modern technology. And there's that number. This is the calculator they're allowed to use on the test. They're like, I don't know how to use something like that. And then we're going to add 2% again. So now you can just multiply by 1.02. Done. So, and then there's going to be rounding. We can talk a lot about rounding. With mortgages, that there's this thing they talk about of finding the additional penny because you have the discrete number, but that's a different question for another day. That's if you made no additional payments. If you got 2% at the end of every year, that's what you would have. Okay? There's a cleaner way to say that because what we did is we took 100 and we multiplied by 1.02, and then we multiplied by 1.02 again, and then we multiplied by 1. So we did it 3 times. So you can just do a little caret or power. 3. Enter. There it is. Okay, so I'm going to erase some of this and make a little note. And this will accelerate quickly, but I needed to do that carefully. So this thing right here, instead of writing that number, I'm going to write that this is going to be 100 times 1.02 to the third, because there will be 3 jumps, 3 times when we add interest. Okay, now in an annuity or something where you're saving money, at the end of each year you contribute money. So let's assume that at the end of the first year we contribute an additional $100. Now often this would be per month, but I'm keeping things simple. So at this moment, we contribute another $100. An interesting thing about interest is if you have like a $100 bill and another $100 bill, and you compute the interest for each. So say you have a $100 bill, and you add 2%, and you get 102. Then someone else says, but I had a $100 bill, and it was in a different bank account, and it also gave me 102. And then someone else says, but I had $200 in a bank account. How much interest did it earn? What's that going to be? It's 204. So whether you keep the money separate or together and compute the interest, you get the same thing. Okay, the point of me saying that is if you add another $100 to the same bank account, you can compute the interest separately. So this new money that we're going to put into the bank a year later, the only difference is it's not going to earn interest as many times. It's going to only earn interest twice. So the final value of that is going to be this. And this is the key stepping stone, is that we're only going to multiply that deposit twice. Okay? And then the next one, let's say we make a deposit at the end of the third year. it's going to only earn interest once. And then lastly, let's say we make a deposit at the end of the story. It's not going to earn any interest. So it's just going to be $100 added on. What we do when we're doing annuities, we add all these things up, and that's the total amount of money in the account. So in this case, it gets pretty messy because you need to do that plus 100 times 1.02. This is really fun to the second. Makes for a good video. Enter. And then we need to add 100 times 1.02. Done. And then we need to add 100. And the total balance at the end of all that is going to be $412.16. And we contributed $400, so the rest of that is interest that we earned. But it's complicated because not all the money had the same amount of interest, so it seems like, ooh, that's going to be really hard. Okay. So here's where the geometric sum comes in. So I'm going to move a few things around here, grab something. And the geometric sum is the following idea, that if it's just a simple little bit of arithmetic if you've never seen it before. Many people have seen this, that if you do the following, and I'm going to steal from my notes here in just a second. Okay, there we go. That's what I wanted to say. Many people know that if you do x minus 1 times 1 plus x. We don't usually write it that way, but it's the difference of squares, and you get x squared minus 1. But there's a more general pattern. You can do x minus 1 times 1 plus x squared, and I would encourage my students to try that and see what happens. You get x, let's write it out. You do x times all those things, you get, maybe we'll do the 1, we'll do the x. You get x times 1, this times this, you get x squared, that times that, and you get x to the third, this times this. And then you do subtracting, you do minus 1, minus x squared. And if you look carefully what happens, these things cancel, and you just get x cubed minus 1. Okay, so let's write that down. We'll get rid of that for a moment. So this is just x cubed minus 1. And it turns out there's a general pattern there. If you go to the next one, this is cool. I've encountered this many times in many math courses when I was a student. This particular bit of factoring comes up in a whole bunch of things. If you rearrange it a little bit, you get this thing here, which is 1 plus x squared plus x to the third is the same as x to the fourth minus 1 over x minus 1. And that is the formula where all the mortgage stuff comes from. So if you think about, now if you go back to our example we just did, I'm going to erase these just so I have some space. What we were trying to compute was the following: 100 times 1, let's say, and then we were trying to do 100 times 1.02, and then we were doing 100 times 1.02 squared, and then we were doing 100 times 1.02 cubed. That's what that was. What do they all have in common? The 100. We can factor it out. And then we have 1 plus 1.02 plus 1.02 squared. And you might say, why am I going into all this trouble? We already computed it. Most of the time when you're doing interest, it's not 4 years. It's 30 years. And not only that, you do it every month. So we need a formula so we don't have to do all these little calculations. And this is where the geometric sum helps us. It's a shortcut. Notice this is exactly what we have. So the mortgage formula is this geometric sum idea, which says we can shortcut all this and just call this 100 and then do 1.02 to the fourth minus 1 all over 1.02 minus 1. That's the formula. That's the formula for saving for retirement. And the mortgage formula comes from a similar place, which I'll mention in just a second. So let's get rid of this. Okay, that's it. That computes it. So remember that number. I'll write it down. So if you're someone that desperately wants me to run an example here. Okay, now let's compute it. So we're going to do it. And I tell students that if you're uncomfortable with plugging things into a calculator, don't ever try to plug it all in. Just do it in pieces. So let's do 1.02 to the fourth minus 1. I think I can handle that. My new thing is, because I see too many students make mistakes, only fill up what you can see and then hit enter. Okay, that's the top. So this is 100 and then it's 0.08. And yes, write it down. That way if you mess up, you have an easy way to check. And the bottom is 0.02. Now, as you do more and more of this, you can do things like, I wouldn't have written it down. I just would have hit divided by 0.02. That's that. And then times 100. Boom, baby. That's the same thing. Okay. So now is when it's helpful of, well, what if you are going to do this for 20 or 30 or 40 years? Okay, that's when it becomes more valuable. Then you can say, when can I retire? This is the formula. So that's it. That's the formula for saving for retirement. And sometimes you have a chunk of money already put away and you just calculate how much interest that earns and then you add on. So if you say, okay, so the truth about the formula is there's an added piece I kind of hid here, which is a bank doesn't give a yearly rate. What they do is they give you some weird number. They'll say like 6, they won't say this because it's too nice, but they'll say 6% compounded monthly. And what they mean by that is that the rate they're going to use is not 6%. It's 6 divided by 12. And in this case, let's use our calculator if we don't know what it is. 0.06 divided by 12. There. So this is the rate they use. Every month they use this rate. That's what the bank means. It's a little weird that the bank says 6% a year when it's not actually 6% a year. It's a little bit better actually. But that's it. And then the number of times you use it, it would be 12 times the number of years. So that's why the formula is typically written, if you wanted to write it in all its glory, you would have a 1 plus r over m. You'd have an mt minus 1, and then you'd have an r over m. But I find that messy to write, so I decided long ago that I would tell students, just compute I and n first, and then you can plug in here and it's simpler. Okay, so if you say, I want to retire when I have $1 million in the bank, then you know the future value you want is $1 million. That's this F. And you might say, well, I only can afford to put in, let's say $500 a year. And I know the interest rate each year is, 6%. And we'll have N be the number of years. And then you can ask the question, when can I retire? And that's just an exercise in solving. It's an exercise in stripping these things away. And I tell students, you can solve if you can just push the right buttons in the right order. Let me demonstrate this. So we have $1 million. I'm going to get rid of the 500. Divide by 500. Successful button push. And then I'm going to multiply by 0.06. Now most students like to write intermediate steps, but at this point you should see I've gotten to here. 1.06 to the n minus 1. And then I'm going to add 1. Well, that wasn't too bad. Didn't need a calculator for that. And then I mentioned this in a previous video. You can't move forward unless you know the button to push, which is the most important function in all of math because it tells you when you can retire. It's this log function. And then there's a rule. So watch my separate video on that if you want. You can divide. So now I need the log of 121 divided by the log of 1.06. 82 years. Oh no, I can retire in 82 years? No. And so then you go back and say, I'm going to change this number to something bigger. Okay, so that's the saving for retirement piece of it. Let's play that game one more time and talk about the mortgage formula. So mortgage formula is a present value question, meaning you have this big chunk of a balance and you're trying to pay it down. So you're trying to subtract $100 from the balance, 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 and then end up with 0. So that's a different question. The question we're asking is, how much are you starting with? So it's more of a reverse engineering question in the following way. So whatever the starting balance is, you're going to multiply. Let's do that 2% again. You're going to multiply by 1.02. 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 So we say, well, that means on the very last day there has to be $100 in the balance, and then you take that away. So we ask it in reverse. We say, in order to end up with $100, what did you have to start with? So we say, what would you have to start with so that if you multiplied by 1.02 4 times, you would get 100? Okay, so that's one thing we'd like to know. That's the money we need to start with so that we have this $100 here. And then we say, but we also need money that makes it so there's $100 here. What's that going to be? So put a little question mark. I don't know. 1.02 to the third. We need that to be this $100 that we extract. And then, I don't know, we have another one of these. 1.02 squared is $100. That's how do we get that money. And then lastly, 1.02. And you would do the same thing if you were withdrawing from your balance. Unfortunately, in the case of a mortgage, it's all bad for you because you're paying it. You're reducing the balance, but it's not helping you. You don't get to keep that money. The bank gets it. Anyways, this is the story. So the question is, what are all those 4 things added together? And so it's the exact same idea, except you have to divide. So the thing we're trying to get, the starting balance that leads to these amounts, first, this you would get by doing 100 divided by 1.02. So we're like undoing the interest. This would be 100 divided by 1.02 cubed. This would be 100 divided by 1.02 squared. And this would be 100 divided by 1.02. We would like to add those together. Okay, here we go. So we would like 100 divided by 1.02 plus 100 divided by 1.02 squared plus 100 divided by 1.02 cubed plus 100 divided by 1.02 to the 4th. Same thing as before. We're going to factor out the 100. And I think, how do we normally do that? Do I want to factor out? Yeah, let's do it. Let's factor out the 1.02 as well. So this is a 1. And then this is going to be 1 over 1.02. This is going to be 1 over 1.02 squared. Let's write it this way. And then 1 over 1.02 to the third. So there's a bit of rearranging here. This is the same formula. It's just, unfortunately, in these spots, we have 1 over 1.02. So it's not quite as pretty. It doesn't immediately give the formula, but we can get it. So it's going to be 1 over 1.02 to the n minus 1. 1 over 1.02 minus 1. And the n here, I shouldn't say n. It's 1 more than whatever it was. So in this case, it's going to be 4. Now, nobody ever writes that formula that way because it's not very user-friendly. So what we do is we distribute here. And that's kind of nice because in the bottom we get 0.02 again. And so what we're left with is this. 1 over 1.02 to the 4 minus 1 over 0.02. Negative 0.02. My apologies for not being very careful there. People don't like to have negatives and negatives, so what people typically do is multiply top and bottom by -1, and then you get this, negative. And you should see this as 1.02 to the -4. And so maybe it's, rather than me try to squeeze everything in, I'll just rearrange it. So you get 1 minus 1.02 to the -4 all over 0.02. So a bit of rearranging. That maybe helps explain why there's this negative in the mortgage formula. It's because you're like undoing the interest. You're saying, well, if I start with that much, how do I get? So that's it. The geometric sum proves all of that. Almost all your financial formulas come from this little observation. Because without it, we wouldn't be able to simplify this long string of things in a nice way. Okay. So let's clean up a little bit and say a few closing pieces. So in practice, what happens in the mortgage formula is they typically give you an interest rate. So let's say your interest rate is 6%. In a mortgage problem, it's always compounded monthly. And they compute the interest at the end of each month. So it's actually more discrete, we say. In most mortgage problems, it's over 30 years. It doesn't have to be. And there are monthly payments. And so if you search online for the mortgage formula, you're going to see this number, 360. And that's important because that's the number of payments you make, which is kind of sickening if you pay it over the course of 30 years. So online, if you search for the mortgage formula, it would look something like this. And you would have a 1 minus 1 plus r over n, or over 12 is what it would be. It'd be r over 12. And then there'd be this negative 360. And then there'd be this r over 12. So if you searched online, that's the formula. And the setup would be, this is your payment amount. This is the starting balance. And so I think in a lot of books, they might call this L for the loan amount. And maybe that P or something else. And often these are the three things you're plugging in if you do an online mortgage calculator. But now you can just do it yourself. What if the rate goes up a little bit? What if I increase my payment a little bit? How will that affect my other pieces? How will that affect my payments? How will it reduce my payments? So often we leave this as N as well. Okay, that's the game you're going to be playing. So it's just nice that you can get it. So one comment I thought I would make, two comments before I leave this, is if you go to my Math 111 page, you can see the things I have for my students on this. Here's the examples from my life that I hand out and everyone throws away because no one cares except one student. Here's my student loans. I do a calculation where I say, using the same formula, you see that formula right there. I say my student loans, the interest rate was about 4.5% monthly. These are approximates. I had about $40,000 in student loans when I was done with college. They spaced it over 10 years, and I had monthly payments. And so the question was, what was my monthly payment? So I plugged everything in. This was my value. This was the interest after I divided by 12. This was the number of payments. I computed all this. I divided. And there's my payments. It was about $400 a month. So I did pay about $400 a month for 10 years. Now, I paid off more early whenever I could, because the more you can pay off early, the less interest you pay. Okay. Then I did an example of saving for retirement. I did my home loan. I approximated. The home loan's kind of sickening because if you figure out how much you're paying, it's way more. The total payments are for this home loan, which was $40,000 down. The question was how much could I do? So if the home loan was $412,000, you end up paying $720,000. It's not quite double, but almost. And then spending your retirement. And then I was just looking, and I found this. This is from 2012. And in 2012, we were stuck in our house. We were in a small house. We had kids sharing a bedroom. The market had fallen out, and we were kind of stuck. So I was trying to refinance, and I made lots of things like this. And I just wanted to show you that since I knew the formula, I was able to put it right in there. Now, it looks messy because I'm doing it in Excel, but it allowed me to play around with it because I talked to a financial person, and they said, well, we could refinance, but you got to get the number down to this. And so I went and figured out, well, what if I get a loan on my cars and I get a loan, personal loan? How much money would I need to get to where I need to go, and how much would I pay it off? And I actually did the calculation like the bank would do it, is I did, okay, at the end of each month, the bank is going to calculate your interest. They take and multiply, and then they take this, subtract the interest you paid, and then that's the part they subtract from the principal. So then I played a game like, what if I subtract a little more off? And you can see I did this at times. Like I paid off extra chunks, if I taught an extra class or something. And I was like, where do I need to get so they will refinance? So the fact that I knew a little bit about this really helped. And I'm not good with money, but I knew the formula. So I wasn't scared of it. I wasn't reliant on someone else to tell me. And what's funny was when I go to the loan officer, they said, well, I just used the calculator. So they didn't know the formula either. So knowing the formula gave me some power. So you can see I tried to figure out how much do I got to do the personal loans? When will the personal loan be paid off? How can I pay extra? So having a little bit of an understanding of this gives you confidence when you go in to talk to a loan officer. Okay. So thank you to my student who asked about this. Hope that's interesting. I just think it's so, to me, surprising that basically the mortgage formulas stem from this bit of math. So that's a pretty big deal for people that are like, I don't see how I'm ever going to use math. If you're going to get a loan, you're using that math, that little bit of factoring. If you're saving for retirement, you're using that math. So this is one that's hard to deny that it won't be applicable to you. I always have students say, but I'm just going to have a financial person that figures it all out. That doesn't work out for most of us. You have to figure a little bit out on your own. And also, do you want to completely trust some random person? And that person goes, oh, you don't know anything about math? Great, I'd love to be your financial person. All right, thanks for listening.